Hello, in this video we're going to start our discussion on alkylation of the alpha position. So we'll be adding alkyl groups to that alpha carbon. So let's look at an example. We'll look at cyclohexanone. And again, we have two alpha carbons, but we'll just focus on one of them because it's symmetrical. And if we add some sort of base first, that will take one of the alpha protons, which will leave electrons behind to form the enolate. And in the second step, we can then add our alkyl group, which will be bonded to a halogen. So that'll be an alkyl halide. And this will give us an alkyl group at the alpha position. So again, once that base attacks or takes the alpha proton, we get this intermediate. So we have an enolate. And then in the next step, that enolate will act as a nucleophile and attack the R group on our alkyl halide, which is partially positively charged, because remember, the halogen is electronegative, so it's partially negative, which makes the alkyl group partially positive. And then electrons will be left behind on the halogen. So would this be SN1 or SN2? SN2, because everything's happening at the same time. So we don't have separate steps, for instance. Now, just a quick note. The alkyl group should be pretty simple. It shouldn't be bulky or difficult to attack since we are performing SN2. So it should be either a methyl carbon primary, or sometimes secondary works too. So let's just say a simple alkyl group. So not bulky. Now, what if our starting material is asymmetrical? What would happen then? So let's say we have something similar to what we saw on the last slide, but this time there's already a methyl group on one of the alpha carbons. So again, we have two alpha carbons, but now we need to figure out which side is favored, what kind of products we're going to end up with. So let's go through the possibilities. So on the right-hand side, I will draw a blue alpha proton. On the left-hand side, actually I'll do orange. On the left-hand side, we'll have orange alpha protons, and let's see what happens depending on which proton we take. All right, so again, in the first step, we're going to add base. So let's draw two different pathways here. So the pathway going to the right will show what happens if we take a blue proton on the right-hand side. And the pathway down below will show what happens if we take an orange alpha proton on the left. All right, so let's focus on the one going to the right. So the blue alpha proton has been taken by a base, so we would end up forming this enolate here. But it does have a resonance structure, right? So we can move the electrons over and show our resonance structure. So in the hybrid structure, the negative charge is shared between a carbon and an oxygen. Now let's show what happens if we take an orange proton. So we'll draw that down below. So we would end up forming a negative charge on that left-hand alpha carbon. And again, we can show a resonance structure for this molecule. Oh, I didn't mean to draw a double bond there. That should be a single bond. There we go. Okay, so looking at our intermediates, which one is more stable? Well, remember, we can look at the double bond, right, and see how substituted it is, and that will tell us how stable our intermediate is, which can tell us a lot about the stability of our products. So let's look at the Enolate Intermediate up above. So after we take a blue proton, we end up forming this double bond here. And how substituted is that double bond? Is it mono, di, tri, or tetra substituted? Tetra substituted. What about if we take an orange proton? We end up forming this double bond that I highlighted in yellow. And is that mono, di, tri, or tetra substituted? Tri substituted. All right, and remember, the more substituted the double bond, the more stable. So our blue double bond, which is tetra substituted, is more stable. Okay, but we're still going to form two products, right? So let's show what happens if we then add our alkyl halide. So we know that we'll add to the blue double bond an R group on the right-hand side. And if we add an alkyl group to the yellow double bond, oh, let me give myself a little more room here. We end up adding that alkyl group to the left-hand side. So which product would be more stable? The one on the right. So that would actually be our thermodynamic product. And what would our other product be? Do you remember the other word we would use? Kinetic. So remember, thermodynamic products are more stable, so they're energetically more favorable, but they have a high activation energy, right? So would thermodynamic products be favored at higher temperatures or lower temperatures? Higher temperatures. What about our kinetic product? Would that be favored at higher temperatures or lower temperatures? Lower temperatures, because the activation barrier for a kinetic product is lower, but the resulting product is usually higher in energy and a little less stable. Now, remember, sometimes the kinetic and thermodynamic products can be the same, but in this example, they're different. Okay. Now, let's talk about how we can favor the thermodynamic product even further. We did say that the thermodynamic product is favored at higher temperatures, but what if we use a particular base to favor that product? So if, let's say we just want to take that blue proton, excuse me, what type of base could we use? Well, that blue proton is sitting next to a methyl group, so, it's kind of hidden away a little bit. So would we want a bigger base or a smaller base? Probably a smaller base to try to favor the formation of our thermodynamic product. What about the orange protons? They're kind of just out in the open, right? So how could we favor our kinetic product? Would we want a big base or a small base? We'd probably want a big, bulky base so that it would definitely take that orange proton over the blue proton, which is kind of in a bulkier space. So let's just write here that we can use a bulky base to favor the kinetic product. And this would also be in combination with the temperature as well. So let's make some summarizing notes here. So we just said that bulky bases favor the kinetic pathway. And remember, we talked about that base LDA, lithium diisopropylamine, and that will form an enolate really easily. So that's a good one to use, and it's bulky. So example given, LDA is a bulky base that forms enolates. So that would be perfect for the kinetic pathway. We also said that the kinetic pathway is favored at lower temperatures. So we would probably want to use a really low temperature like negative 78 degrees Celsius. Now, if we want to favor the thermodynamic pathway, then we're going to use a small base at moderate or high temperatures. So small bases at moderate or high temperatures favor the thermodynamic product. So a really good base we could use that's very small is NaH, sodium hydride, or lithium or potassium hydride, any of those hydride bases. And then we could just use room temperature. Okay, so let's look at some more examples. So given what we just went over, If we want to favor the formation of the thermodynamic product, we can use NaH at room temperature, and then we'll follow that with our alkyl halide, which again should be a simple alkyl halide or relatively simple. If we want to favor the kinetic product, then we're going to use LDA at negative 78 degrees Celsius, followed by a relatively simple alkyl halide. Okay, so now we have even more tools in our tool belt for synthesis problems, which we'll talk about at the very end of the chapter. Next time we're going to talk about a synthesis called malonic ester synthesis. So I will see you then.